Hello future engineers, welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends. That's one way you can keep me going, inspired and refreshed. Now, if you find my videos interesting and important to your studies, also please don't forget to subscribe. Level 95, the plane region A is submerged in a fluid of weight density gamma. The resultant force of the fluid pressure on the region is R, acting at the point C called the pressure center, located at the distance h below the surface of the fluid. Show that this R is equal to specific weight of the fluid or weight density of the fluid times QA, where QA is the first moment of area, and H is IA over Q sub A, where IA is the second moment of area about the axis AA. So here is the given figure, and that's a region of area A. So let's have a strip, horizontal strip for our solution. So since the every element or every point on this strip is equidistant from the water surface or from the liquid surface, the pressure intensity would be uniform as shown. So the area is dA, that's the pressure intensity, we call that P. And from fluid mechanics, that pressure is simply specific weight times distance of that differential area or point from the liquid surface. And if the distance is denoted by y, then pressure P is specific weight or weight density gamma times y. So P is specific weight of fluid or weight density of fluid times y. Then the resultant force acts at the center of pressure C. The differential force acts at the centroid of this pressure diagram, dr. And from the figure, or R is equal to the integral of dr, and dr is equal to pressure times differential area. So dr is pressure times differential area, where pressure is gamma times y, specific weight or weight density times y, and dA is just dA. So R therefore is integral of pressure, which is weight density times y, or specific weight times y. Y is that vertical distance there, dA. Since specific weight or weight density is constant, we put it before the integral sign. Then we have weight density times integral of y dA. So from calculus, this integral of y dA is the first moment of area, which is equal to area times or QA. So that is QA. If this is the centroid of the area, then that's the moment of area, first moment of area with respect to axis AA. So that is actually equal to area times HG from the figure. So QA, or area times HG. So we have shown that R really is specific weight or weight density times the first moment of area. So that's it for the first part. For the second part, we use the second moment of mass, that is R times H equals integral of moment arm of dr is y, and times the force, differential force dr. So replacing R by specific by weight density times QA times H equals integral of y, then replacing dr by specific weight times y dA. Then we cancel specific weight, so QA H equals integral of y squared dA. After we cancel weight density, this quantity here, so QAH equals integral of y squared dA. Then from integral calculus again, from calculus, This is the second moment of mass or the moment of inertia of the area with respect to axis AA, and we simply denote this by IA. So QAH equals IA, therefore H is IA over QA. And that proves this statement. Level 96, the panel shown forms the end of a throw that is filled with water to the line AA prime. Using the results of level 95, determine the depth of the point of application of the resultant of the hydrostatic forces acting on the panel, which is the center of pressure. So here is the given figure. Take note, this is the water line section. This is the water level, and which is exposed to the atmosphere, so zero pressure. So for our solution, we have to locate the centroid first. So this was the result in level 95. So H sub c, the distance from the water surface to the center of pressure, denoted by HCC, is the moment of inertia of this section with respect to axis AA prime divided by the first moment of this area with respect to AA prime. So Q A prime AA is simply area of this triangle times distance of centroid to the axis AA prime, and that is h over 3 because this is a triangle. So that's the centroid of the area, and that's h over 3. Then this is the center of pressure C, and the distance is h sub c as shown in the figure, where I prime AA, or the moment of inertia of this section with respect to AA, is simply the moment of inertia of a triangle with respect to the base, and that is base A, height h cubed over 12. So take note of that. While QA prime AA is the moment of area, first moment of area with respect to A prime, and that is area of that triangle, 1/2 AH, then times distance of its centroid to that axis, h over 3. So I prime AA is again BH cubed over AH cubed over 12, while Q prime AA is simply area of the triangle, 1/2 AH, then distance h over 3. So simplifying this, which is 6 over 12, cancel AH squared, so h over 2. So h sub c is h over 2. Level 97, the panel shown forms the end of a throw that is filled with water to the line AA prime. Using the results of level 95, determine the depth of the point of application of the resultant of the hydrostatic forces acting on the panel, which is the center of pressure. So here is the given figure. Again, this is the water line level AA prime. And we have two areas here, composite, rectangle, and triangle. So let's divide the area into the manner shown. So this is the axis of symmetry, vertical axis of symmetry. The centroid lies here. So for rectangle, the dimensions 2b by h, the centroid is here, and the distance of the centroid from AA prime is h over 2. For the triangle, the centroid is here, g2, then this is 1/3 of h, then 1/3 of h plus h, the distance of g2 from the waterline level is h plus h over 3, so that is 4/3 of h as shown. So h sub c, the location of the center of pressure C is here, and the distance from AA prime is h sub c as shown. So h sub c is, by the results of level 95, moment of inertia of the section with respect to AA prime, or IAA prime, divided by the first moment of area with respect to AA prime, or QAA prime. So h sub c is IAA prime, or IA prime AA plus QA prime AA, where IAA prime is moment of inertia of this rectangle with respect to AA prime. So it is just 2b h cubed over 3. Remember that? Moment of inertia of rectangle with respect to the base. Base 2b, height cube over 3. Then for this triangle, we have to transfer the centroidal moment of inertia with respect to this axis to that axis there. So for the triangle, it is 2b h cubed over 36 plus area of the triangle 1/2 of 2b times h, then distance square, which is 4/3 h quantity square. So h sub c is equal to 2b h cubed over 3 for the rectangle, then for the triangle, plus quantity 2b h cubed over 36 plus area 1/2 of 2b times h, then distance 4/3 of h quantity square, divided by qa prime. So this is simpler. It is just area times moment arm or distance of the centroid from the axis aa prime. So it is just 2b times h, so divided by, for the rectangle, 2b times h, that's the area, then moment arm h over 3. For the triangle, 1/2 of 2b times h, then distance 4/3 of h. So the numerator would be bh cubed and the denominator would be bh squared, so leaving the variable h in the numerator. So 2/3 plus 2 over 36 plus quantity 16 over 9 bh cubed divided by bh squared plus 4/3 bh squared. So simplifying, that would be 5 over 2h in the numerator, and in the denominator 7/3 after we cancel bh squared. So simplifying further, h sub c is equal to 15 over 14h. So that's it. Level 98, the panel shown forms the end of a throw that is filled with water to the line AA prime. Using the results of level 95, determine the depth of the point of application of the resultant of the hydrostatic forces acting on the panel, which is at the center of pressure. So here is a quarter circular section. This is the water level AA prime. And for our solution, let's locate the centroid first, which is 4r over 3 pi from the axis AA prime, and the center of pressure C, which is not directly below G, not directly along the line through vertical line through G. It may be rightward or leftward, so I think it's a little bit rightward. But what is important is the vertical distance of C from the water lines section, water line level, which is at AA prime. And we will denote that by h sub c. And h sub c, remember, is equal to moment of inertia of the quarter circular section with respect to AA prime divided by the moment of area of quarter circle to axis AA prime. So h sub c is I prime AA over Q prime AA. I prime AA is moment of inertia of a quarter circle with respect to A prime, and that is just pi r fourth over 16 because this is a quarter circle, while QA prime AA is area of quarter circle times distance of its centroid to that water level, which is 4r over 3 pi. And the area of the quarter circle is, of course, pi over 4r squared. So again, IA prime AA is pi over 16 r to the fourth, while QA prime AA is pi r squared over 4, then times 4/3 of 4r over 3 pi. So cancel pi, and simplifying, it is 3 pi r over 16, or approximately 0.58 90 of R.